Hello, and welcome to another edition of Math Teacher to Go. Today we're going to look at our third of 3 videos about the basic concepts of function notation and graphs. And our objectives here today are to determine the domain and range of a relation that's given as a graph, and determine the domain of a function given as an equation. We won't work with the range of equations right now because there are other ways to do that we'll learn later, but the more important part is the domain. What numbers can go into the equation and produce a valid result. So you might remember that domain went with x coordinates, or the horizontal axis, and range went with the y coordinates. So our first objective, finding the domain and range of a function given as a graph. On the graph, the inputs are labeled, and the horizontal axis will call this x, but it doesn't always have to be x. And the outputs are labeled on the vertical axis, and we'll call these y. The domain is the set of all allowed inputs to the function. Now, when we had function notation, we had like a function might be called f, and then you'd have the parentheses x. That tells you the x's of the inputs. So that would be, the x's that are allowed into the graph. Any x value that has a point on the graph associated with it is in the domain. The range is the set of outputs these allowed inputs create. Any y value that has a point in the graph associated with it is in the range. So there's 2 basic types of domains and ranges we're going to look at here. One is what we call discrete, and that would be points, not paints, points, and separated. They're separated. There's no line connecting the points. The other type would be continuous. That means there's a line connecting the points, and we couldn't possibly list all the x values. So just keep that in mind. When we look at a graph that's points, our domain is going to be a list of x coordinates. When we look at a graph that's points, our range is going to be a list of the y coordinates. So hopefully I just wanted to erase this, but it's not going to eraser mode. Alright, never mind. I won't erase that. So find the domain in the range. This is example 1. Find the domain in the range of the function below. So domain are all of the numbers that are represented by points, all the numbers on the horizontal axis. So I can see I have a -4, I have a 0. Oh, I skipped one. It looks like there's a -2 there. See, the -4 has a point that goes with it. The -2 has a point that goes with it. The 0 has a point that goes with it. The 2 and the 3. So the domain is a set. We put sets in braces, and we list each x coordinate that would appear if I listed all the points in this graph. -5, -2, 0, 2, and 3. So these are the x coordinates of the points. It might be easier for you to label all the points and then write down the list of x's, or make a list of the points and just write down all the x's as we did in previous lessons. The range, now this is a set of points, so we get a list. It's the y coordinates of those same points. So if I look at the graph, I can see this first point has a y coordinate. It looks like that's a 5. This one's at 7. This one's also at 5. The range repeats. That's okay. It can still be a function for that. It looks like I have a -2, a -1 for this point. So I'm going to make that list. And the first point on the left that I see over here has a y coordinate of 5. And I'm going to move left to right. The next one has a y coordinate of 7. Then I have a -2 for the y-coordinate. Then I have another 5. I don't list things twice in a set. You only list them once. And in a set written in braces like this, order doesn't matter either. So the y-coordinate of that last point right here seems to be a -1. So that is how I answer the question, what is the domain and range of this function when the function is simply a graph of individual points? It is a list. So the x goes with the domain, the y goes with the range, as we've discussed before. Now, but if you have a graph, that's what we call continuous. Now, this isn't continuous everywhere. You'll learn more about continuous, but it's continuous from -9 to 6, not including the -9. But I can't possibly list every x-coordinate that's represented on the graph. I've got a point there, I've got a point there, I've got a point there, and all the points in between. There are an infinite number of them, so you can't list them. So we write our answers as an interval. So when I'm looking at domain, I'm looking at what x's are shown on the graph. Well, the leftmost x is at -9. So when I do the domain, I'm going to start at -9, and it's not included because of the open circle. And then I look in every x-coordinate in between, and it doesn't matter that it goes up and down, but look, every x-coordinate has a y graphed with it all the way out to 6. So we go from -9 to 6, and the 6 is included because it's a solid circle. So I would write that in interval notation with a rounded parenthesis for the -9. -9 is the left, 6 is the right, and I get a square bracket there. Now when I look at the range, I'm looking at what y coordinates are there. So I tend to look for the lowest one. And it looks like y = 1 is the lowest, and it is included. So I'm going to start. So when you do range, you do lowest to highest. That's the exception to when we did interval notation. We always said left comma right. It's going to be low comma high for range. So the range starts at 1, and then the highest point I see anywhere on the graph seems to be at y is 7. And because the graph looks like it goes through both of those, I will include both of those. So that's the range. Y is between 1 and 7, including 1 or 7 in that interval. So when you have a graph, you list your domain. When you have a graph of a connected set of points, you use interval notation for the domain and range. When you have a set of points, you just give a list. So because these are points that are individual, you list the domain and the range. So let's take a look at some practice problems. Now we have that one and that one. So we have two practice problems similar to what you just did. I'd like you to stop the video and try those and come back. Okay, you're back. So you must be ready to see the results. So for the first problem, I have a list of points, and the domain is going to be all the x-coordinates listed. If you forget the squiggly brackets on the test, I'm not going to be upset about that, but I do want to see a list if it's points. So it looks like I have an x is -5, I have an x is -4, I have an x is -1, I have an x is 2, and I have something plotted at x is 4. So I think those are the x-coordinates of each of these points, so that's the domain. And the range will be the y-coordinates of those same points. The first one here is y is 6. The next one looks like y is 3. The next one is y is 0. The next one, it looks like y is 2. And the last point, y is negative 3. So I list the domain and range as individual numbers because I have points. Okay, so let's move on to problem 2. Now this is a graph where everything's connected, so you're going to give an interval. It's a little bit of a trick to this one. We didn't see any arrows before. So the meaning of this arrow means this graph, if I graphed on a larger grid or included more values, would keep going up while it keeps going to the left forever. So that means at the top point of this graph is negative infinity. So y approaches negative infinity is how I should say that. And the left end of the graph, y approaches positive infinity. Y is going up. So that goes to positive infinity. The left end, x goes to negative infinity. So if there's an arrow, you're going to have an infinity involved. If the arrow's over here or pointing down, it might be different for whether it's a left or a top. But so for the domain, my x values start at negative infinity. If I kept growing this graph and went, so I showed like 50 on the y-axis and negative 50 on the x-axis, I would see this graph just kept going. But if I look at the other end of the graph, I have a closed circle, so I know the right end is going to be included, but I have to figure out where that is. So if I look to get the scale here, I seem to have cut off the scale there, but you have enough information. That's a negative 10, so it's 2, 4, 6, 8, 10. Each grid is 2. So I have 2, and this appears to be out in the middle. That's at x is 3. So the domain goes from negative infinity to 3, and the range is from the bottom to the top. So the bottommost y looks to be negative 12.5, we'll call it, and I won't be too fussy. So the bottom is negative 12.5. That might be a little generous, might be more like 0.3, but that's close enough. And the top of the graph, it's tempting to say it's here, but it's not. Remember, this keeps going to positive infinity. So my range starts at the low is negative 12.5. I put a comma, and I put the highest point is going to be infinity. You can never actually get to infinity, so I put a round parenthesis. Okay, well, I don't know why that disappeared, but so if you're having trouble with those, you should see me for help and or ask some questions in class. The second objective of this video is to talk about how do we find the domain of a function from its equation. So domain is the set of values that can be put into the equation for x and generate a y coordinate without breaking any math rules. The big math rule that you should be aware of is you cannot divide by 0. And because domain refers to the real number system only, we can't take square roots of negative numbers or any even root of a negative number. So any x value that would cause that is not allowed. As you learn more functions like logs and trig functions, you will also learn more domain rules about equations. But for right now, those are the two big ones. So sometimes a function tells you its domain. Here's your function, and it just says, only use this function between negative 1 and 6 for x. Students get really confused. They say, I don't know what to do. It's just telling you, you can't put 10 into that equation because it's not between negative 1 and 6. This gets used a lot in scientific and in physical and engineering applications where a model might only be good for a certain set of values or certain temperatures. But if this wasn't here, this domain would be all real numbers. We'll talk about that in a minute. But sometimes your domain is restricted by the function stating it outright. That's not usually the case, though. What if it's not stated explicitly? How can I figure out what x values can be put in? So you're just told, well, you can't even use -1, but you can use any number between -1 and 6 to put into this function. But what if you're not told? How do you figure it out? So we're looking for the input values that produce a real number, and it's easiest to figure out what numbers you can't use, and then basically say you can use everything except these numbers. So we cannot create division by 0, and we cannot take an even root of a negative number. So whatever is inside our radical symbol, if this is a square root or a fourth root, must be positive. And positive means it has to be greater than 0. 0 is not positive. So actually, I take that back. We could be positive or 0, because you can take the square root of 0 at 0. So you're going to take whatever's inside there and only allow numbers to be put in for your variable that will make that greater than or equal to 0. We will talk about that in a moment. So polynomials. Well, polynomials basically are equations, functions you've used so far that don't have any possibility of putting in a number for x that causes division by 0 or the square root. So the form is some number times x to a power plus some other number times x to 1 power less plus, and you go all the way down until you get plus a number. We call that a0. That's a polynomial. These numbers can be fractions, but there's no x's in the bottom. There's no fractional exponents. There's integer exponents, and there's no variables appearing in denominators. So they use multiplication, addition, subtraction, non-negative integer exponents. These operations will always result in a real number no matter what real number x you put in. So we say the domain of polynomials is all real numbers. So this is not a complete list for all of your math career, but it's what we need for now. So if I need to find the domain of example 3, I need to say, are there any rules I could break? Could I pick a number that would cause division by 0 or the square root of a negative? Well, if I look, anytime you have a variable in a denominator, you've got the possibility of dividing by 0. So what has to be true of this function is the bottom cannot equal 0. So you write down the expression that's on the bottom of that fraction, the denominator, and you write cannot equal, just an equal sign with a line through it, 0. And you solve this. So I'm going to add 4 to both sides. X cannot equal 4. So that tells me what I'm leaving out of the domain. So I can use any number from -infinity to infinity if I draw a number line, but I have to leave out the 4. So I actually need 2 intervals to express this. So the first interval is all the way from -infinity to the 4, but not including the 4. The second interval is from 4 to infinity, not including the 4. So I write that with interval notation for both of those places, both before and after the 4. And notice this parenthesis around each 4, because I'm going to go up to 4, but not include it. And then I'm going to start at 4 without, just a little beyond 4, without touching it, and go to infinity. And sometimes we write a union in there. Your online math homework might have a comma. But this is the same as saying x cannot be 4. So that's the big new idea here, is that you look at the function, there's a variable in the denominator, so you have to figure out what would make that denominator 0 and say you can't have that, the way you figure out what it would be, where it would be 0, is to solve an equation or an inequality. So look at example 4. You say, oh, I've got denominators. Yeah, you do, but there's no variable in this 3. There's no variable in this 19. Fractional coefficients are okay. They don't give any trouble. So there's no possibility of dividing by 0, and I don't see anything looks like that anywhere in the expression at all, and definitely not one that's got an even index, like a 4, or we don't write the 2, but it's there if we just write that. So since there's none of those, let me erase this. I don't have the possibility of dividing by 0. I don't have the possibility of an even root of a negative. So we say the domain of this polynomial is all real numbers. And the way we say all real numbers in interval notation is negative infinities on the left and positive infinities on the right, just the ends of the number line. So that's example 4. That's a polynomial. Don't be tricked by that. There's not always something you can't use. Now, example 5. When we write a radical symbol, we have h of x equals the square root of 3x minus 6, and only the 3x minus 6 is in the radical. That's worth looking at. But we do not write the 2 when it's a square root. That's the most common radical we use, so it's implied that there's a 2 there. That is called the index, and that's what makes this what I'm calling an even root. So the 3x minus 6 has to be non-negative. It has to be greater than or equal to 0. Otherwise, I will be taking the square root of a negative number. So that still doesn't tell me what I can use for x, so I have to solve this. So when you have an even radical, you write it inequality with just what's inside the radical. Equality with just what's inside of the radical greater than or equal to 0. Notice I did not add the 4 because it's not inside the radical. And I solve this. So when I add 6 to both sides, I get that. I divide both sides by 3. It's a positive 3, so I don't have to worry about flipping the inequality sign there. I get x is greater than or equal to 2. So that radical is the only restriction I see. I don't have division by a variable, so there's no possibility of dividing by 0. So x is greater than 2 would be my domain, greater than or equal to 2. And in interval notation, that puts a 2 that's included on the left and infinity on the right. So that's when there is an even root. Now let's compare that to example 6. They look very similar. But what's important to notice in example 6 is the index of the root is a 3. Think about what that means. That means a number that I multiply itself 3 times and get what's inside. So if you take the number 8, if I multiply 2, write down 2 3 times and multiply, I get 8. Can I take the cube root of negative 8? Yes, I can, because when you multiply 3 negatives, you get a negative. The problem with the even roots is you're always multiplying an even amount of numbers together, and each pair of numbers creates a positive no matter what the sign of the original number was. Here, if you have a negative, so it is possible to take the cube root of a negative number. So the domain of this, because it's an odd root, odd numbers end in 1, 3, 5, 7, and 9, the domain of this one is all real numbers. There are no other difficulties. I don't see any other division by 0 going on. There's no t's in the denominator. So we get, again, all real numbers is the domain for this. And that means negative infinity to infinity. And that's how we express that in interval notation. Now I have a couple for you to try. There's problem 3, problem 4. Try those, stop the video, and then come back when you're done, and we'll take a look at what the solution is. All right, you're back. So this first one, remember the two things we're checking for are, could I cause division by 0 with putting in a number for x? X is not in the denominator anywhere, so there's no possibility of dividing by 0, and there's no radicals at all. So this happens to be a polynomial, so the domain is all real numbers. And we express that in interval notation with negative infinity, comma infinity, surrounded by round parentheses. Now, problem 4. This has a couple of things going on. Remember, the two things I need to investigate is division by 0. I can't have that happen. And I can't have, well, in this case, I have a square root, so square root of a negative. So both of those could happen here if I put the wrong number in for x. I want to find out what those wrong numbers are so I can keep them out. So let's look at division by 0 first. In order to end up dividing by 0, it would mean 2x plus 3 would have to equal 0. So that doesn't tell me what x would be to make that happen. So I can't have it equal 0. So I'm going to write that as an inequality. So I solve this as if it were an equation. I'm going to subtract 3 from both sides. I get 2x cannot be negative 3. And then when I divide both sides by 2, I get x cannot be negative 3 halves. So x can't be negative 3 halves. And now if I look at the top, I have a square root. So I need 0 or larger inside of that. I can't have a negative number. So x must be greater than 5. Now I have to combine these two things. It's not too bad because x greater than or equal to 5, well, I'm not going to ever get negative 3 halves anyway. So this becomes my domain. If this had been positive 3 halves, I would have had to, no, actually then it wouldn't have been a problem. But if this had been a number bigger than 5, like 7 over here, I would have had to start at 5, leave the 7 out, and then go from 7 on. But greater than or equal to 5 gives me a square bracket and a 5, a comma, an infinity, and a parenthesis in interval notation. So that is how I find the domain. Don't try to look at the problem all at once. Remember the two things you're looking for. Is there any way I could put a number in for x that would cause division by 0? Because there's an x in the bottom of a fraction, that's a possibility here. So I have to do this over here. Now, the other thing is, do I have an even radical? Yeah, there's no number here, so that's a 2. So whatever's inside that radical has to be greater than or equal to 0. So I get x greater than or equal to 5, and then I can write that in interval notation. But if I look at that, I got x not equal to negative 3 halves. Well, if it's bigger than 5, it will never be negative 3 halves anyway, so we don't have to worry about that beyond that check. Okay, that's it for part 3 of our function work. This domain stuff from equations tends to cause students more difficulty than I wish it would. Just remember the two rules. If you have a denominator with a variable, you write an equation with the denominator not equal to 0, solve it, leave the whatever number you get there, leave that number out. If you have an even root with variables inside of it, whatever's inside of that radical symbol has to be greater than or equal to 0. And you solve that to find out what you can have. All right, well, let's see you in class. That's it for this edition of Math Teacher to Go.